All right, let's get started. So today I want to do two things. First of all, I want to talk about your second exam that is coming up either Wednesday or Friday for everybody, and then we could talk about related rates if anybody has any questions over the related rates section. So let's first of all just talk about our exam coming up and what to expect. So exam number 2, review. So on our last exam, we actually did define, we already had the definition of the derivative, and we took derivatives using the definition, like what I mean is like the limit of a difference quotient. So on this exam, I'm not going to expect you to do that at all. Okay, so any derivative that I ask you to take on this exam, you can just take the derivative. You don't have to do any limit of f of x plus h minus f of x over h. That won't be on this exam at all. So any derivative on this exam, just take the derivative and you're good to go. So what kinds of things have we done? Well, we've learned about the power rule. We've learned about the product rule, the quotient rule, the chain rule. Then after we got through kind of, those are some of the major rules, then we talked about derivatives of trig functions. We've done derivatives of inverse trig functions. We've done derivatives of exponential and log functions. We've used implicit differentiation. And we just are getting done with related rates. So let me just give this a quick look and make sure I didn't miss anything here. Yeah, that looks pretty good. Okay, so these are the kinds of things that we've been studying since the last exam. And so the majority of problems on this exam are just going to be me asking you to take a certain derivative, right? And you might have to use one or more of these things to take that derivative. So the best way to go about this, the things that I can promise you will definitely be on the exam is I'll definitely put an implicit differentiation problem on the exam. You can expect that. And I'll definitely put exactly one related rates problem on the exam. I won't do more than one. So there'll be one related rates, one implicit differentiation, and then just some like, do you know your derivative stuff? So do you know all the derivatives of trig functions, inverse trig, exponential log, all of that stuff. So these will be maybe the more substantial problems on the exam, and then some little problems just to make sure that you know all your rules. Okay. Any questions? Yeah.
Will we be allowed like a note card for all the Trig reviews, or do you have to have it memorized?
You need to have them memorized. Yeah.
And you want us to know all of them, right?
Yes. So like in terms of rules to know, like the power rule, of course, we've used that 1,000 times, but then you need to know the product rule, quotient rule, chain rule. There's 6 derivatives of trig functions, right, to be known, right? Inverse trig functions, similar. There are 6 of those. Derivatives of exponential and log functions. Well, basically you need to know how do you take the derivative of an exponential? How do you take the derivative of a log? So that's kind of like 2 more. So, you know, you've got like 12, 13, 14, 16 or 17 different rules that you need to know. But these are all things that you're going to just use, not just in this class, but in Cal 2 and Cal 3, differential equations, if you go that far. You'll just use these things over and over and over again. So it's good to just know them. So that's why I don't do a note card for this exam. Is it's kind of like, it's a bummer when you're in calculus 2 and you're like, what's the derivative of secant of x? You know what I mean? It's kind of like, well, you should know what it is. Okay, so that's it for this exam. The test will probably be about 10 problems, give or take, if I feel like it's getting too long. Any other questions about the exam? Yes, sir.
The implicit differentiation problem will like clearly be labeled, or like we'll just kind of have to know that.
It probably, I'll say something like use implicit differentiation to find the derivative of. Yeah, probably it will be labeled, but it's usually pretty clear because it isn't like y equals x stuff. It's a mixture. So either way, but usually I will write use implicit differentiation. Yeah.
When exactly is the exam going to be?
What's that?
When is the exam?
Oh yeah, when is the exam? So we're doing it the same as last time, and correct me if I'm wrong, but I believe that groups B and C took their exam on Wednesday, and group A took their exam on Friday. Is that, well, they didn't end up taking their exam on Friday, but that's when it was supposed to be. So it's going to be the same, yeah. So Wednesday. Will be groups B and C, and then Friday will be group A. Okay. Other exam questions for me? All right, very good. Any related rates problems that you would like me to look at?
I have a question about number 38.
38?
Yeah.
Okay. $38. Yes. So the 2 tanks problem. Yeah. A specific question, or did you just a general, how do you do it type
Well,
question?
I mean, it is kind of specific, but it's kind of hard to explain without like writing the problem.
Okay.
Yeah.
Okay. Let me get this written out a little bit. Okay, so 38. So we have these 2 tanks. So we have kind of like a conical tank at the bottom. And then we have a cylindrical tank on the bottom, and on the top we have a cone. And then down here we have some water, in this tank as well. Bring down. Okay. And we know that this is 4 meters across. We know that the cone here is 5 meters high. We also know that the cylinder is 5 meters high. Okay. And then it says conical tank with upper radius 4 meters and height of 5 meters drains into a cylindrical tank with radius 4 meters and height 5 meters. Okay. If the water level in the conical tank drops at a rate of 0.5 meter per minute, at what rate does the water level in the cylindrical tank rise when the water level in the conical tank is 3 meters or 1 meter? Okay. Okay, so the interesting thing about this problem is it's kind of like asking us 2 problems, right? So first of all, we have to figure out something about the conical tank, and then we have to figure something out about the cylindrical tank. So we know that water's draining, and it even gives us something. It says that it's draining if the water level in the conical tank drops at a rate of 0.5 meters per minute, then we should be able to find something about like the amount of water that's draining out of the tank, or like dV dt. And that's what we need, because we need to know how fast water is coming into this tank, which is also dV dt. So what I'm going to do is I'm going to just forget about this tank completely right now and just look at this tank. So here we can call that little r, and the height of the water, or whatever fluid is inside, we can call little h. And then what is the volume of a cone again?
1/3 pi r squared h.
1/3 pi r squared h. Very good. Okay, and we've kind of dealt with this before. Even in our last class, we dealt with a cone and how we could use similar triangles to get rid of one of the variables. So we want to do that again. And we know something about the rate at which the height is decreasing, correct? Yeah, the water level in the conical tank is dropping at a rate of 0.5 meters per minute. So we know something about dH dt. We don't know anything about dr dt, and we'd like to find something out about dV dt. So if we could get rid of r, that would be very helpful. So we know that like h divided by r is the same as 5 divided by 4. Right, by similar triangles. So now we could solve this equation for r and get rid of r in our equation. So if we solve this, we get 4h equals 5r. And then if I solve for r, I get that r is 4/5 h. So now I'm going to take that value for r and plug it in right there to get a new volume formula. So I get that volume is equal to 1/3 pi r squared, but r is 4/5 of h, 4/5 h squared times h. Okay, I'm going to move over here, I think. All right, so now we can simplify that a little bit, and we get that the volume is equal to, let's see, 4/5 squared is 16/25 times 1/3 is 16/75. 16/75. Does everybody agree that that would be the constant? Definitely on top of 16, bottom is 25 times 3. Yeah, that's good. So 16/75 times pi times h cubed. And that's about as good as it gets. And so now we're ready to take a derivative. So if I take a derivative of this equation with respect to t, I get dv dt is equal to, bring down the 3. I can, let's see, 3 times 16 is 48. So I could write this as 48 over 75 pi h squared times dh dt. All right. And the goal here is to find dv dt, right? Because I want to know how fast is the liquid falling from the upper container into the lower container. So in order to find dv dt, I need to know what h is, and I need to know what dh dt is. So do I know that from the problem? It says, let's see. Yeah, when the level of the water in the conical tank is, first of all, they say 3 meters, then they say 1 meter, correct? So let's start with 3 meters. So if h is 3, what's dh dt?
Oh, negative 1/2.
Negative 1/2. That's right. They give it as 0.5, but the water level in this tank, the volume is going down as it drains, right? Not up. So it needs to be in there as a negative number. And so we get that dv dt is equal to 48 over 75 times pi times h, which we said was 3, times dh dt, which we said was negative 1/2.
3 squared.
Thank you. 3 squared. Very good. Okay. So what do we have now? Do some things cancel. So I could certainly cancel a 3 with this 75 to get a 25. Anything else?
48 and the 2.
Yeah, 48 and a 2, I could make this a 24. Cancel that 2. Might be as good as it gets. So I get negative, let's see, 24 times 3 would be, what's that?
72.
72, very good. Over 25 times pi. And does it make sense that the rate of change here is negative? Yeah, because the volume is going down, not going up in that tank. Okay, so what we just figured out is, and we could put units on this if we want to, but we figure out how fast the liquid is draining from the tank. Well, the rate at which the liquid is draining it from the tank is the same level that it's going into this tank, right? So now we know what dv dt is for this lower tank, but it should be positive, right? Because in this tank, the level is going up. So we just changed the sign, and now we know what dv dt is for the second tank. So if we're looking, now we're switching gears, and we're looking at the second tank, and we need a formula for the volume of a cylinder. What is that? Very good. Pi r squared h. Okay. What do I know about the radius of the cylinder? Yeah, it's 4, right? But as the water level goes up and down, does r change? It's constant, right? It doesn't matter where I am at this tank. Here it absolutely does. As the water goes down, the radius changes. Here, as the water goes up and down, the radius stays the same. So r, in this case, is always going to be 4. So I can plug that in. So I get that v is equal to pi times 4 squared times h, or if you like, v is equal to 16 pi h. Okay, so now I could take the derivative of both sides of this with respect to t, and I get that dv dt is equal to, well, 16 pi, and the derivative of h is just dh dt. And I know what dv dt is, right? Because I just solved for it over here. dv dt is 72 over 25 pi. So this dv dt that I'm looking for is 16 pi times, oh, I'm sorry. That's the one I know. This is 72 over 25 pi is equal to 16 pi times dh dt, which is what I'm trying to figure out.
Isn't it negative?
This one? Good question. It is negative on the top tank because the volume is going down in the top tank. But as it runs into the second tank, it should be positive because it coming in should be making the volume go up. Does that make sense? So the pi's, of course, cancel on both sides. And what are we left with? We have the dh over dt is equal to, let's see, the 16 go into 72? Not as well as we would like. So we've got 72 divided by 25 times 16 is equal to, oh, that's our dh dt. And what would be the units on this?
Meters per minute.
What's that?
Meters per minute.
Yeah, the height is measured in meters. The time in this problem is measured in minutes. So dh dt should be around 72. It's a pretty small number. Okay. Any questions?
So what kind of like formulas do we need to know? about
Yeah.
this?
Okay, for this exam, that's a really good question. People always are wondering, like if I give you a related rates problems, what kind of like geometry do you need to know? And this is what I will say about that. If it's three-dimensional, if I ask you to work with a three-dimensional shape like a sphere, a cone, something that like that, then I'll give you the formula, okay? If I ask you to work with something that's two-dimensional, like a rectangle, a triangle, a circle, those kinds of things, I'll expect you to know the formula for anything in 2 dimensions, okay? So if it's on the plane, it's on you. If it's 3-dimensional, I'll provide it. Does that sound good? So just your basic geometry, I'll expect that you know, like that the area of a triangle is 1/2 the base times the height, something like that you would need to know. Something like this, I would give you the formulas you need. Yes, sir.
Is it difficult to go when you do something like this?
I mean, it's not that I don't think you could do this problem, but I think this would maybe take a little longer than I'd like it to take on the exam. So I think I can probably say no, just based on the amount of time I would expect that problem to take. So, but I could ask you like the first half, you know, like if it was just draining out of the cone, maybe I want you to find this dVdt. That would be appropriate. Yeah. Although I've got to admit that, you know, I went to George Fox and I remember my second Cal 1 exam, and the problem was like this. I remember on that exam because it was such a hard problem. I still remember the problem. It was very, very mean. It was there were 2 carts, like on like a track, and then there was a pulley and there was a rope attached to the pulleys, and you pulled one cart, and you said if you pull this cart at a certain rate, then how fast is this cart going when it's so far away from like this center point? And so you had to like do two problems, because you had to like this pulled this, which pulled this, which pulled this, and it was mean. I won't deny that. So anyway, yeah, I would say it will only have one differentiation part, if that makes sense. Yes,
What do you go for 43?
43? Okay, let's look at it. The shadow. Okay, so 5 foot tall woman walks at 8 feet per second toward a street light that is 20 feet above the ground. Okay, 5 feet tall. Okay, so we've got like a street light, and then we've got somebody out here. They're 5 feet tall, and the street light is casting probably shadow. Okay, so what is the rate of change of the length of the shadow when she's 15 feet from the street light? Okay. And then at what rate is the tip of her shadow moving? So what rate of change is the length of the shadow when she's 15 feet from the street light? Okay. So what I need to do is I need to set up some variables here. I know that this height right here is 5, right? Is it 5 feet? And that the street light is 20 feet tall. Then I need to set up some variables. So I'm going to say that the length of the shadow, because that's what I want to find the rate of change of, right? There's different ways that I could set this problem up, but I want to know what's the rate of change of the length of the shadow. So I probably better assign that thing a variable. And so I'll call that X. And then I also could say, what else do I know about? Probably how fast she's moving towards the street light, right? So I'm going to call the distance from her to the street light, let's call that Y. Okay. And now what we have is we have two similar triangles. We have this triangle and we have the big triangle here. And so I can set up an equation using similar triangles that, let's say, x divided by 5 is the same as x plus y divided by 20. So x over 5 is the same as x plus y over 20. And now I could cross multiply if I wanted to, and then I could get 20x is equal to 5x plus 5y. I could subtract 5x from both sides, and I get 15x is equal to 5y. And I could even divide both sides by 5 if I wanted to, and get that 3x equals y. That's about as nice as a equation gets before you want to take its derivative. So now we could take the derivative of both sides, and I get that 3 dx dt is equal to dy dt. And something that's kind of cool in this equation is that the x and the y go away, right? So this problem, the dx dt and the dy dt, don't really have anything to do with the distance x and y. They just have to do with each other. So if I know one, I can find the other. And I do know one. What do I know? In this case, I know that she's walking toward a street light at 8 feet per second. So what is that? What's changing that's 8 feet per second? What's that?
Yeah, the one.
Y, yeah, so y is changing, so that's dy dt. Is it a positive number or a negative number? Negative, because y is getting smaller. So dy dt should be what? -8. So I say that 3 dx dt is equal to 8. So in other words, dx dt is equal to 8/3. Now, what's the unit? Oh, I'm sorry. Did I say -8? We said -8. Sorry, missed that.
Could you put it as dx dt and have it be positive?
No. Could you plug it in here as a positive 8? No, because dx dt is the length of the shadow. So when you say how is x changing, and that's what I want to find, right? Is how fast is the length of the shadow changing? So dx dt is not 8, because that 8 is how fast the distance between her and the street light is changing. Make sense? Okay, so yeah, that was -8 divided by 3. I get -8/3. And what's the units on that? X is measured in what in this problem? Feet. And time? Is it measured in seconds? Okay, feet per second. And so that's telling me that the shadow itself is shrinking at a rate of -8/3 feet per second as she walks towards the streetlight. Yeah.
So in any of these related Briggs problems, you always plug in the constants into the initial equation and leave the variables of the changing numbers.
Correct. So you always, if something is changing, then it needs to be left in until a derivative is taken, right? If something, the only time that I ever plugged anything in was like over here, where I said that I could plug in the radius of that cylinder. And the only reason I could do that is no matter what happens, that radius is fixed. In this case, well, certainly the distance y is not fixed as she walks. And certainly the length of the shadow is not fixed as she walks. So I need to leave those variables in until after I take a derivative. Then you can plug in for those after the derivative is taken. But you've got to be a little bit careful not to start plugging things in before you've taken a derivative. Yeah. Yeah.
The problem says like her clothes and her changes like now when she is 15 feet away from the street light. When does the 15 feet come into play?
Yeah, it doesn't. So that's a good question. And why doesn't it? Normally in these types of problems, it would. But in this case, when you take the derivative of 3x equals y, the x goes away and the y goes away. So what that means is that the rate of change of her shadow is independent of how far away she is from the street light. So if you changed it and it was like, well, what if it's not at 15? What if it's at 10? Well, that means that this rate of change is constant as she walks. So it doesn't matter where she is. That's going to be the rate of change of the shadow. Does that make sense? Yeah. So it just doesn't matter where she is. Yeah. 38? Yes.
It says what rate is the water level in the cylindrical tank rise when the water level in the conical tank is 3 meters?
Yes.
And then 1
Yes. So we did 3 meters, right? So the only change that would happen is at some point I plugged in that, let's see, where was it? I guess it would have been the next step. That I would have simplified this a little bit more, and then I would have plugged in that h is 3, right? After taking a derivative, I would have plugged in that h is 3. What they're saying is do it again, except this time let h be 1. Okay, so you can just go back to that step where you plugged in that h is 3, plug in h is 1 instead, and see how that changes the answer. Okay. There is like a second part to this problem where they're talking about the tip of the shadow to the street light, and that does change it slightly. Do you want me to go over that? Okay. Okay, so what I would do if I were changing it, and now we want to know how fast is the tip of the shadow moving towards the street light? Well, I would just change how I set up my variables. So instead of making that x and y, what I would do instead is I would just make the distance from here all the way to here one variable. Okay, so let's call it, let's say, x. And then what I could do is I could say, let's make the distance from the lady to the street light, let's call that y. Because I know something about dy dt, so I want to get that distance involved. But instead of making this x, let's make this x. Because now I want to know dx dt, right? What's the change of the tip of the shadow to the street light? Okay, so now it's kind of similar, but a little bit different. Because what is this distance now? Yeah, that's x minus y. So this is x minus y right here. So now I still have similar triangles, just like I did before, but now my relationship is x minus y is to 5 as x is to 20. So I could say that x minus y over 5 is the same as x over 20. So now I could cross multiply again and get 20x minus 20y is equal to 5x. So I could move the 5x over here and get 15x is equal to 20y. Divide both sides by 5, and I get 3x is equal to 4y. Right, now I could take the derivative of both sides. You get 3 dx dt is equal to 4 dy dt. I still know what dy dt is, right? It's -8. So I can plug that in and I get 3 dx dt is equal to 4 times -8. And now I could solve for dx dt, which now is so dx over dt in this case will be 4 times -8 is -32 divided by 3. And that's still in feet per second. So that would be my answer. So the key in these problems where those are two slightly different questions that they answer, that they want you to answer is, how do you set up your variables so that when you take the derivative, you're getting the right rate of change? Does that make sense? Okay. Other questions? Yeah.
I had something, so about 50.
Yes.
When you're moving it from the tangent theta to the secant squared, yeah, I just kind of get confused about that part. When you're...
Oh, yeah. So I did this one a little bit right the other day. And so you're saying when I moved from tangent theta, like when I was taking the derivative?
Yeah, so you don't need to find, how do you find theta for the secant?
Oh, yeah. So what I did, and you don't have to do it this way, is I didn't try to find theta, although you can. So I think I got something on that problem like, that it was like tangent theta is equal to, do you remember what I wrote?
Yeah.
X over 500. Okay. So there's a couple different ways that you can go about messing with this problem. One of them is, as I did it, I think, and I just took the derivative of this. Is that right? I just took the derivative as is. The other thing you could do is you could say that theta is tan inverse of x over 500. And then you don't have to deal with the secant squared theta because you're not taking the derivative of tangent anymore. But now you do have to deal with taking the derivative of tan inverse of x over 500, which is also kind of complicated on that side. So it just depends on which way you want to deal with things. If I do take the derivative here and I get secant of theta, well, what I can do is I can use the triangle that's formed by the lighthouse and the shore. So in this problem, there's the lighthouse up here, right? And it's shining a light. There's a point here, there's a point here. This is an angle, we're calling it theta, correct? And then we've got, this is what we're calling our x, and this was our 500, correct? And I think that at the point where we care, what is it, 200 meters? So x is 200. So if I wanted to know what's secant of theta, I don't have to know what theta is. Okay, because what I can do is I can say, well, secant of theta is 1 over cosine of theta. Cosine of theta is the adjacent over the hypotenuse. So the adjacent side is 500. The hypotenuse is, well, I don't know what the hypotenuse is, but I could figure it out using this right triangle, right? I could say that if I wanted to call this side z, that z squared is equal to 200 squared plus 500 squared. And then I could figure out what z is. And then I could say that secant of theta is just going to be the, what did I say? This is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So it's just going to be z over 500, whatever z is. Right, so once you've solved for z in this Pythagorean theorem, plug it in here, then you get what secant of theta is, and you never even have to know what theta is.
Oh,
You just have to know what secant of theta is.
oh, because then you just square, so then you would square secant of theta.
That's right. Then once you know what secant of theta is, you can square it and plug it into your formula. Does that make sense?
Yeah.
So if you go the other way, like I said, and go here, then when you take the derivative, you just get d theta dt, and you never need to know what theta is because you don't have any theta show up in the derivative. So that actually comes up a lot when you're using trigonometry, where you don't actually ever have to know what the theta is if you can use the triangle to figure out like what the secant of theta would be or the tangent of theta would be. Yeah. Did that answer your question?
Yeah.
Okay, awesome. Okay, I think that's a good place to end for today. So have a good day, study hard for the exam. Just a reminder, math lab is open 7 to 10 o'clock at night in Lemons 15. If you need any extra help in the next couple nights, yeah.
It's actually the 5 to 9.
5 to 9? Oh, they changed it, okay. So 5 to 9 in Lemons 15. So definitely use that as a resource if you need a little extra help. They are happy to help. Okay, have a good day. I will see you on Wednesday or Friday.